Hello everyone, I'm Aditi Kinkhabala from New LJ Institute of Engineering and Technology. Let us continue with the topic of stacks. So, in today's lecture, we are going to see the last application of stack, which is recursion. So, students, let us start with the basic definition of recursion. Recursion is a process of defining large and complex problems in terms of smaller and more easily solvable problems. Right? So basically recursion is the concept of function calling itself. Right? So a recursive function is defined as function which is calling itself. We all know that if we want to write recursive function of factorial, we can write as factorial, right? So if n is equal to 1, then we'll return 1, else we'll return factorial n into factorial of n minus 1, right? So we will return n into factorial of n minus 1. So basically this is a function fact and we are calling the same function in its logic, right? In within this curly braces we are again calling factorial, but this time instead of n we are making the problem smaller, that is n minus 1. Again it will repeat, again it will become n minus 1. So basically we are dividing a large problem into smaller and easily solvable problems. So we are decreasing the number. So as recursive function repeatedly calls itself, it makes use of system stack. We have seen this in the first lecture of stack, that when one function calls itself or some another function, all the active functions are stored in the stack, right? So basically system stack is used to temporarily store the return address and local variable of the calling function. Now students, every recursive solution has two major cases. Whenever we write a recursive function, we should keep in mind that it definitely has a base case. What is the base case? So we can say base case is the terminating condition, right? So we want one situation where the problem or recursion should end. Without that, it might go into infinite loop. Now, for example, if I say 5 factorial, so 5 factorial is what? 5 into 4 into 3 into 2 into 1, right? So it ends at this 1. So while writing the recursive function for factorial, we can see that we have written here if n double equal to 1. So this is the last case, n double equal to 1, we return 1. And that answer basically, that answer will be going to n minus 1. That is, if we say factorial of 5. So what is factorial of 5? So it will return 5 into factorial of 4. Then what is factorial of 4? 4 into factorial of 3 and so on and so forth. At the end we would have factorial of 2 into factorial of 1, and this factorial of 1 will give us 1. That 1 will be multiplied by 2. 2 in 2 ones are 2 would be multiplied by 3, which will give 6 into 4, which is 24, into 5, which is 120, right? So this is how factorial works. So there are two cases. One is the base case, which is compulsory in order to terminate or in order to solve the last solution, and that solution will in turn return the answer, and that answer is will be used in corresponding function calls. Now the second major case is the recursive case, where we actually call the same function again. So this is factorial, and when I am calling this factorial again but on a lesser number, that is n minus 1, this is a recursive case. So every recursive function has two cases, which is base case and a recursive case. Now let us see what are the types of recursion. So there are many recursions such as direct recursion, indirect recursion, excessive recursion, nested recursion, tail recursion, non-tail recursion. So let us see some of them in brief. Now direct recursion is basically a function which explicitly calls itself. Okay, so a function calling itself directly is called direct recursion. For example, we can see here a function name is there, right? Func. And within its bracket, if we are again calling the same function, as you can see here, function n minus 1. So the function is calling itself. So this type of recursion is known as direct recursion. That is, a function explicitly calls itself. Now, the next one is indirect recursion. So, a function is said to be indirect recursive if it contains a call to another function which ultimately calls it back. Now, if we have this function, as you can see, within this function, we are calling not the same function, but this time another function, which is function 2. So, function 1 is calling function 2. Now we have this logic for function 2, and within that logic, again function 2 is calling function 1, right? So this is called one kind of indirect recursion, wherein actually function 1 is calling itself but not directly via some another function. So function 1 calls function 2, and function 2 in turn calls function 1 back. Okay, so that is what it is called as indirect recursion. The third type of recursion is tail recursion. Students, a tail recursive function is said to be, basically a function is said to be tail recursive if no operations are pending to be performed when the recursion returns to its caller, right? So when the function returns to its caller. So basically, let us see this by example. So basically, tail recursive is that there are no operations performed after the function is called, and everything is printed and output is printed before the function is called. For example, in main, function 3 is called, right? So basically, function 3 is called function 3, right? Now function here, this is 3. If n equal to 0, 0, we just have to return. Else we have to print n and return f of n minus 1. So what will be the output here currently? Print n. So output would be 3, and we are calling n minus 1. So we are calling function 2. Again, this will become 2. N is not equal to 0. So we are printing 2. Again, n minus 1 is called. So f of 1. This is 1. Again, not equal to 0. So we are printing 1. Return function of n minus 1, and this time we have function 0. As soon as n becomes 0, this if condition becomes correct, that is n double equal to 0, and we are just returning to the calling function. So f of 0 returns to f of 1, f of 1 returns to f of 2, f of 2 returns to f of 3. Okay, output is already printed on the screen, and we are just returning the function. Other than that, no operation is performed while it is returning back, right? So this kind of recursive function is said to be tail recursion, which is ultimately at the end, after which no operation is performed. Every operation is performed before it. We have printed the output as well. So while returning to the calling function, it does not perform any operation. So this is what it means by tail recursion. Now the next is non-tail recursion, which is the opposite of the tail recursion. So a recursive function is said to be non-tail recursive if whenever there is a pending operation to be performed, right? So we have seen the example of factorial. So that is again a kind of non-tail recursion, right? Why non-tail recursion? Because if we call factorial of 5, if we call factorial of 5, what is that? N into factorial of 4. Then 4 into factorial of 3. 3 into factorial of 2. Similarly, 2 into factorial of 1. As soon as factorial of 1, n equal to 1 is encountered, we will return 1. So this gives answer 1. 1 into 2 is 2. This 2 is returned over here. 3 2s are 6. This 6 is returned over here. 6 4s are 24. And this 4, This 24 is returned in factorial of 5, and 24 into 5 is 120. So first, this one to get solved returns some kind of value. So in non-tail kind of recursive function, whenever the function is called, it returns some kind of value and operations are still remaining to be performed. So once it returns the value, then the next operation can be performed with the help of this first one. So this is a part of non-tail recursion. Now students, let us understand the difference between iteration and recursion. Again, let us take the same example of factorial, how we can solve factorial using iteration. So iteration means repeating same process again and again. So iteration basically uses loops, right? So if I say for I equal to 1, I less than equal to n, I plus plus, so what is the factorial? Factorial is equal to fact multiplied by I, right? And the same thing we have just seen how we can write in terms of recursion, factorial of n. So if n equal to 1, we have to return 1, else we have to return n into factorial of n minus 1. So iteration, students, basically involves loops, and factorial using recursion basically have function calling itself, right? So iteration is a process of repeating, that is executing statements repeatedly until some condition is satisfied, whereas recursion is a technique defining anything in terms of itself, that is function calling itself. So iteration involves 4 steps, which is initialization, we need to give condition, we need to execute some statements, and we need to update, that is I plus plus. And here in recursion, there must be an exclusive if statement inside the recursive function specifying the stopping condition. We definitely must have base condition inside recursion. Any recursive problem can be solved iteratively, but reverse is not true. Not all problems have recursive solution. Next, iterative computer part of problem is more efficient in terms of memory utilization and speed. And recursion for simple problem, it is sometimes can get quite complex. Even though size of writing the program is smaller in recursion, iteration is a bit easier to understand, right? So these are the differences between iteration and recursion. One of the major applications of recursion is the Tower of Hanoi. So this is a problem which is a kind of puzzle which can be solved using the concept of recursion using stack, right? So Tower of Hanoi is basically, we can say it is a mathematical puzzle which consists of 3 towers, which is 1, 2, or 3, or ABC, source, destination, auxiliary, we can name it anything. So it has 3 pegs. So this is definitely fixed. It has 3 pegs, and then there are 3, 4, 5. There could be n number of discs on the one peg, and our main aim is to transfer all discs from source to destination. Now these rings are of different sizes and stacked upon each other in ascending order. That is, size are different, and the smaller one is always at the top of the larger one. Okay, so there could be different variations of Tower of Hanoi, with n could be 2, 3, 4, and so on. But number of towers will be remaining fixed. That is, there has to be only 3 towers. Right? So what is this problem and how it is solved using recursion? Let us see that. So in our main aim, what is the main aim or goal of this? We have to transfer this 3 disks from source. If this is the starting point, then this is the destination. So we have to transfer from source to destination, and we can make use of this auxiliary, which is kind of a temporary or we can say temporary tower, or used for in between operations. Okay, so in order to transfer all disk from 1 to 3, there are three rules that we need to follow. So the first one is only one disk can be moved among the towers at any given time. Also, we can only remove top disk. We cannot remove the last ring or last disk before removing the first one. So we have to always remove, because stack is last in, first out. And no large disk can sit over small disk. So small disk always has to be on the top of the large disk. So based on these three rules, in minimum number of steps, our aim is to transfer all the disk from 1 to 3. Okay, so we should take the minimum number of steps possible, right? And we should follow these rules. So now let us trace what when we have three disks on A, right? A, B, and C. So what is our first step, students? We need to transfer. So our last output is this, right? So we need whatever is there on A, we need it on C. So first, let's see, we will start with shifting from A to C. We are shifting disk 1 from A to C, so it goes over here. Then we are shifting second disk 2 from A to B, right? Because we want this last one to to go from A to C. For that we have to empty the n-1 also, right, into some other tower. Now what will happen in step 3? This again, this first ring is now going from C to B. So it is now going from C to B. You can see here. Now A is remaining with one disk and C is empty, and this one is largest. So the fourth step is removing disk 3 from A to C. So directly we have shifted it from source to destination. Now we need to place B over here. So B, on B we have 1 also, so we will shift it here. So the fifth step is we will shift 1 from C to A. Then we will shift this white one from B to C. So second from B to C, and last, first from A to C. So this is how we need to shuffle the disk and get all the disk onto the destination tower, right? And that too in minimum steps. So it is required that it could take more steps also, but we need to solve in minimum number of steps. So ultimately the logic of this recursion is that if we have this kind of situation, right, where we have three disks, so what should we do is we should come to a situation where A only has one disk and C has no disk. In that scenario, when A, that is source, has just one disk, it can simply transfer that to C, right? So if n is equal to 1, that is on source, if there is just one disk, we can easily transfer that disk from source to destination. Okay, but what if it does not have one disk and have greater than one? So what is step 2? Step 2 is this situation, that it has more than one disk. In that scenario, what you have to do, students, move n-1 disk, right? The last disk, which is the nth disk, whenever it is alone, that is whenever n is 1, it will directly be shifted from source to destination. Otherwise, if this stack, source stack, has three different disks, we have to shift all the remaining, that is n-1, from source to some middle auxiliary value. Okay, so we are shifting this to some auxiliary intermediate. If this is B, so we can shift it to B using C, right? Using C. So C is our destination. We can make use of C, but for this n-1, they should go into B. Now again we are left with 1. If n-1 are shifted to B, we are left with one disk at A, and that will be transferred to C. So we will move from source to destination, right? And now again these remaining disk will be shifted from B to C using A. A here is source. Students, S, D and A in this steps means source, destination and auxiliary. Okay, and here A is what? Source, B is auxiliary and C is destination. So ultimately, logic of Tower of Hanoi is that if there is just one disk, we can simply transfer from source to destination. But if there are total n greater than one disk, what we have to do? We have to shift the n minus 1. Other than last, all the disk we have to shift to the auxiliary tower, and then when we are left with just one, we can shift it to destination, and then all the remaining inside auxiliary are shifted one by one. So this is how Tower of Hanoi recursion works. Let us see the algorithm for the same. So it takes 4 argument. N is number of disk, it could be 2, 3, 4, anything. S is source, auxiliary and destination. Now students, as we have just discussed, if n is 1, that means we can directly transfer the disk from source to destination, correct? If n is 1, we can directly transfer from source to destination. Otherwise, if n is not 1, n is greater than 1, in that situation, what we just discussed, in that situation, we have to remove this n minus 1. And where we have to place it? We have to place from source, right? We have to place from source to auxiliary, right? Source to auxiliary. Where is source, students? This is S. So destination is currently for n minus 1, it is A, and we can make use of D, destination. Okay. So students, you should see this. Second argument is source, last argument is destination, and the third one argument is the um, third argument is the auxiliary, right? So for remaining n minus 1, we have to transfer from source to destination, in this case is auxiliary, and we can make use of the uh, D, that is destination, as auxiliary array, right? And now after n minus 1 is shifted, we are just remaining with 1. So we will just transfer it from S to D. Now, what about the other remaining C? Just a second. So after this situation, what will happen, students? Here, first of all, we have 3. Okay. So we have 3 rings. Now, n is greater than 1. So we will call this. So n minus 1 will be shifted from source to destination is auxiliary array. Okay. So this is source, this is auxiliary, and this is destination. So after implementation of this, what will be the situation? Here it would be 1, here it would be 2, and here it would be destination, right? And now we are just remaining with 1. So we will print S to D. So this would be from S to D. And now how we can transfer this? So we can, source is auxiliary, this is destination, and we can use source. So what is the source, students? Source here, see this is source, second one is source. So here second one is source. So A works as a source. So auxiliary has the elements that has to be transferred to destination. Fourth one is destination. In our scenario, destination is D, and we can take use of auxiliary array, and in this situation auxiliary array is the S, right? So now remaining elements are also transferred. So this way, if we trace the algorithm, we can get the steps of shifting disk from A to C, that is from source to destination. Quickly let us understand this based on source, auxiliary, tower and destination. So initially we have A, B, C, N is 3. Okay. So this is source, this is auxiliary, and this is destination. Okay, we can also say like this is A, this is B, and this is C. Now we have this A, B, and C. We will call this function n is not equal to 1. So we will call this function 2, right? And now for transferring these two, what is our destination? A, right? So our destination source is A, source is A, source is A, source is A. What is our destination, students? Destination is B. So destination is B and we are making use of C. Again, this function is in turn. So again, this function is in turn calling this function. So now it would be 1. Okay, so when we just have 1, so that one disk would be transferred from A to C, right? So first of all, this will be printed A to C, and then what will be printed? A to B, then C to B. Fourth one is A to C, B to A, B to C, and A to C. This is how all the 7 steps are traversed by recursion, that is calling this function again and again. On sometimes source is same and sometimes source becomes different. Similarly, destination changes as per what disk we are transferring, whether we are transferring the last disk or the remaining disk. So basically for 3 disk, maximum steps are 7. So this was all about the topic of stack. We have gone through all the operations and applications of stack. Thank you.